Welcome. In this session on natural deduction, we'll explore the semantics of functions. A function is, in our terms, it's a map. And we'll say it's a map into the non-empty universe of discourse, which is A. That is, we can write a function, but when we get to talking about the semantics or the meaning of a function, what we mean is a map. And we can have various kinds. When we're writing these in proofs, we can have, for example, a Nullery function. And that can be written either as f, or we might want to write f and then have a pair of parentheses with nothing inside to indicate that this doesn't have an argument, but it is a map. And that means that whenever we write f, there's a specific object in the universe of discourse that it will return to us. Another example is a Unary function. And this is a function that maps an object in the universe of discourse to an object in the universe of discourse. And we might also write that as something, for example, f of a term. And we would take that term and evaluate that term. That term would be the argument, and then we would find the function's object that corresponds to it. A function might be binary. And we would write that as f of, in mathematics, so now we're thinking in our meta logic, which is set theory, A cross A to A, and we might write that as f of term 1 and term 2. Another way that this is often written is f, we would say that this is A squared to A. And we could have ternary and so on. So when we get to an Unary function, that is a function that has n arguments. And that is written as a function that goes from A cross A n times and maps into the universe of discourse. And we write that using as many terms as are needed. So let's suppose that we have, this is Unary, so we have n terms. So we could write this in either way. When we get to the semantics, what we'll do is we specify a function, and when we specify the function, it now has to be within a model. Let's look at an example which is base for arithmetic. So in that, there are 4 objects in that universe of discourse. There's 0, 1, 2, and 3. And if we want to start our arithmetic off somewhere, it would be useful to have one element that is always found. We might start, for example, at 0. And we might define the Nullery function I, which is in the model that we're gradually building, and we will say that equals by definition 0. And so what we would do is, no matter where I appears, we can always substitute this specific concrete object in the universe of discourse. And that's a way that we could index into the set of base 4 numbers. We might then define a Unary function, and we could call this the successor function. And we could define that as S of a term is, and that's in our model, is defined as, we could say that is t plus 1 modulo 4. And if we wanted to, we could even do this by enumeration because our set is not only finite, it's quite small. So we could say that the successor of the index is 1. And we could say that if we take the successor of the index and we take its successor, that equals 2. And so we're relying on the semantics of equality here, and we can now see that there's an infinite number of ways to specify 1. We could define a new Nullery function, for example. We could call it U for unity, and it would always return the value 1. We could say that wherever we see 1, we'll substitute the successor of the index. And of course, if we did this 4 times, we would wrap around, and so we could write 5 of these S's in a row of the index, and we would still end up at the object 1. So this now allows us this very powerful idea of there's a Nullery function that picks out a particular object in this universe of discourse, and then we have 1 or 2 or as many arguments to functions as we need, and we specify these using rules, and within our metalogic, which is a set theory, we can easily represent these rules, and so we're able to describe the semantics of a function in natural deduction.